It is my pleasure to virtually welcome Robert, who will be talking to us about the meta C-Finite Ansatz.
Okay, thank you very much, Steve. Good afternoon, everyone. Sorry that I'm not in person how I promised to be. I woke up feeling a little glum this morning, and I thought it'd be better to not expose everyone to my bad feelings. So instead, we have Zoom, we have email, it's great. It all works out fine. So my talk today is in some sense about identities and how you discover them and how you prove them. I think that identities are some of the most marvelous things that we have in mathematics. You know, integral evaluations, summations, recurrence relations, sequence identities for Fibonacci fans. And I think it's worth looking at some of those. So here's an example of one. A very famous identity involving Fibonacci numbers, Cassini's identity. You take a Fibonacci number, you square it, and that square is going to be very nearly equal to the product of the two adjacent Fibonacci numbers. In fact, it's going to be better than very nearly equal. It's going to be off by exactly 1 every time. And better than being off by exactly 1, it will be 1 too big, then 1 too small, then 1 too big, then 1 too small, going back and forth forever. And this is what Cassini's identity says, written out here as an equation. Now, this is a pretty neat identity. I think it's cool in and of itself, but more than just the identity, I think it's a really good example of how you can try and prove these identities. What are the techniques that you have? Because the techniques for proving identities are often just as exciting and fascinating as the identities themselves. So if you were to give this to, say, some poor undergraduate, you know, their first day at university, welcome to class, prove Cassini's identity. At least in America and most places, they would probably try and check a couple of cases. Check n equals 1, check n equals 2, check n equals 3. And they go, oh, look, there's a pattern. You know, done. Great. I can go get lunch now. If you give it to like a slightly more sophisticated undergraduate, maybe after a couple of years of studying, they might try and do some inductive proof. And if you do an inductive proof, of course, it works out exactly right. It relies on this identity here. If you move the square over to the left-hand side, it turns out you can replace n with n minus 1 everywhere. You just pick up a minus sign. So as long as you start off plus or minus 1, you flip-flop back and forth, plus or minus 1 over and over and over again. And you prove this identity by looking at the square, you apply the Fibonacci recurrence, you expand some things, you FOIL some stuff, and do some simplifications, and it all works out just fine. And in some sense, I guess induction is the right way to do it. It feels sort of morally correct. Like I have an identity involving non-negative integers, I should probably do induction or something like that. It feels right. But I have to admit that I feel a lot more in common with the naive undergrad who doesn't know any better. The one who just tries to check it. Just check a finite number of cases and notice a pattern and say, we found a pattern, let's call it a day. And the reason I feel that way is because that undergrad is really onto something. When it comes to Cassini's identity and lots of other identities that we'll talk more about, you actually can prove this just by checking a finite number of cases. You only need to plug in a few values of n to show that it's true for all n, no induction required. And that's because Cassini's identity is only using sequences that are called C-Finite sequences. Now, I don't know if everyone is familiar with this vocabulary, probably with the concepts, maybe not the vocabulary though. A sequence is C-Finite if it satisfies a linear recurrence relation with constant coefficients. So the nth term of the sequence is some linear combination of the previous few terms, where I only multiplied the previous terms by constants. And however many terms I have to go back that I have to use, we call that the order of the sequence. So obviously the Fibonacci numbers are a C-Finite sequence because every term is the sum of the previous two terms. So it's second order and the constants are both 1 in this case. The Lucca numbers are also C-Finite. They satisfy the same Fibonacci recurrence. They just start somewhere differently. Fibonacci, Quaternacci, any recurrence that you write down, C-Finite. Not everything is C-Finite, of course. Factorials are not C-Finite. They satisfy a linear recurrence, but the coefficients are polynomials, not constants. Harmonic numbers are not C-Finite. Bernoulli numbers are not C-Finite. in some sense, there are more things that are not C-finite than that are R. But when you're working with C-finite sequences on their own, you get a lot of really amazing properties. And they're especially useful when you're trying to prove identities. Now, why is that? Because C-finite sequences satisfy these really wonderful closure properties. If I take two C-finite sequences, I can add them, subtract them, multiply them, or convolve them. And the result is always another C-finite sequence. And what's a little bit better is that I can actually put a bound on the order of the resulting sequence in terms of the order of the two sequences I started with. And also, you'll notice the first line here is not an operation with two sequences. It's sort of shifting and dilating a sequence. That also stays to be C-finite. So these closure properties are already, they tell you some pretty neat things that are not so obvious on first glance. For example, because the Fibonacci numbers are C-finite, that means that the square of the Fibonacci numbers is also C-finite. So the square of the Fibonacci numbers satisfies some linear recurrence relation with constant coefficients. Now, that's not that hard to prove if you sit down and you play around with it a little bit, but this tells you it's automatically true, and it's not because of the Fibonacci numbers, it's because of the recurrence that they satisfy. And what's neat about this is you can start to glue expressions together to get more and more complicated C-finite sequences. For example, of course, the square of the Fibonacci number is C-finite from the closure properties, but then if you start to put pieces together, here we have square of a Fibonacci number minus the product of the two adjacent Fibonacci numbers. This is also C-finite by using the closure properties. And this is a very interesting sequence to know that it's C-finite, because that's exactly the expression that we're looking at when it comes to Cassini's identity. So let's take a look at Cassini's identity again. So Cassini's identity here, if you take it and you move everything over to the left-hand side of the equation, what you're really trying to say is that a given sequence is identically equal to 0. So whatever this expression is here involving Fibonacci numbers and exponentials, it should be 0 always. And the closure properties tell you that this sequence satisfies some linear recurrence relation with constant coefficients. And what's great about satisfying such a recurrence is that if you are 0 for enough initial conditions, you're 0 everywhere, forever. So to give a totally rigorous proof of Cassini's identity, you would just need to show that it holds for enough initial values. Then it would automatically hold for all n after that. And really, the only question left over is how many values do you have to check? Of course, we know Cassini's identity is true. So in some sense, of course it's true. But if you were starting from scratch and you didn't know Cassini's identity was true, you can use the closure properties to put an upper bound on the order of the recurrence. It would look something like this. The Fibonacci numbers are order 2. So products of Fibonacci numbers, order less than or equal to 4. Square of a Fibonacci number, order less than or equal to 4. And an exponential term is C-finite of order 1. So altogether, the left-hand side of Cassini's identity is C-finite of order less than or equal to 4 plus 1, which is 9. So all you have to do to prove Cassini's identity is check that it's true for n equals 1 up to n equals 9. And if that's the case, which of course it is, Cassini's identity is true for at least all positive integers. Maybe for negative integers, you need to think a little bit more. But for positive integers, you're done. Now, this is very different than the inductive proof. I didn't really show the algebra for the inductive proof. But if you wanted to go prove Cassini's using induction, you really have to get your hands a little dirty with the structure of the identity. You have to look at it and go, well, what can I try here? What can I do? What do I see? What can I make this look like? How can I, come up with some clever trick to turn this into what I want to? And this proof here doesn't even try to do that. It does nothing sophisticated at all. It just says, check that it's true. And it cares very little about the structure of the identity itself, other than that everything involved is C-finite. So what that means is that this proof technique applies to almost any identity that you would write down involving Fibonacci numbers. And here are three other ones. These are nothing groundbreaking. These are very famous identities. The sum of the Fibonacci numbers, Benet's formula, and some of the squares of the Fibonacci numbers. All three of these identities are provable in exactly the same way that we just said how you would prove Cassini's identity. I would say, okay, move everything over to one side. Everything involved is C-Finite. So all I have to do is check 10, 20 terms, and that's a proof right there. Now, any finitely generated C-Finite identity should be routine to prove in exactly the same way, with no real mention of induction or the exact structure of the identity. Now, what I like about this is it feels almost like some kind of a moral statement about when you're working with C-Finite sequences. It says something like, if you conjecture an identity involving C-Finite sequences, you've probably also proved it at the same time. Because to prove the identity, you just need enough data. You just have to check that it's true for enough terms. And you wouldn't have conjectured it if you didn't have enough data to prove it, probably. That's not always true. Sometimes you conjecture something that you don't have enough data and it turns out to be wrong. But for C-Finite sequences, it's almost always the case that it's good and it works out. So this is why you can use C-Finite sequences in proving identities. And this is where they're really the most powerful, using these closure properties. Before we get too far ahead, though, I wanted to mention that when we use the closure properties in the proof of Cassini's identity, we use them sort of abstractly. We didn't really write down the recurrence that the sequence satisfied on the left-hand side. We just said there exists a recurrence. But in fact, the recurrences implied by the closure properties are very effective. We can compute them, and it's not even that hard to do. It gets a little tedious to do by hand, but I thought I would show you an example here of how you would find a recurrence for the Fibonacci numbers with an even index. So the closure properties guarantee that this sequence f of 2n has to satisfy some recurrence. And this is how the proof of the closure properties basically goes. So I create two dummy variables, x and y. So x is f of 2n and y is f of 2n plus 1. When I do that, I can write down this system of equations here. So the system of equations, the first one is just sort of by definition. The second one, you apply the Fibonacci recurrence once and you get x plus y. The second one, or the third one, you have to apply the Fibonacci recurrence twice. And when you do that, you end up getting 2x plus 3y. And the reason that this is helpful is because this system of equations is linearly dependent. I can find a non-trivial linear combination that gives me 0. And keeping in mind what the left-hand side is, that actually implies a recurrence. So you'll notice that it's going to be the third equation minus 3 times the second equation plus the first equation will be 0 by canceling x and y on the right-hand side. So if I translate that back into what the equations represent in terms of Fibonacci numbers, that gives me a recurrence here for the Fibonacci numbers with the index divisible by 2, the even indices. And this is essentially the proof of the f of m times n plus I, shifting and dilating. You basically do this. You just have to wave your hand a little bit and say, and you'd keep unfolding over and over. Here we had 2, so we only had to unfold the recurrence once, but maybe later on you have to do it more times. But it's pretty straightforward. It's so straightforward you can write a program to do it, and then you never have to do it again by hand. And I did that. So here are the first few recurrences for f of m times n, where m goes from 1 to 5. So Fibonacci numbers with indices divisible by 1, by 2, by 3, by 4, by 5. These are all gotten from the same method as before. It's completely rigorous, no guessing here. This is just automatic proof stuff. And what's neat about this is as soon as you start writing down equations aligned like this, you start to see patterns, right? Look at the coefficients in these recurrences. So how do I describe this? The coefficient on the term furthest to the right is alternating between plus and minus 1, plus 1, minus 1, plus 1, minus 1, plus 1. And the coefficient on the first term after the equal sign, it's not alternating, but the terms are 1, 3, 4, 7, 11. And these are the Luca numbers. So by writing down this system of it's not a system, but this list of recurrence relations for the Fibonacci numbers, it seems like we've found some conjecture, some general pattern of recurrences where maybe the first coefficient is always going to be the mth Lucas number, and the next one is always going to be minus 1 to something like that. And so this written out, this is what it actually is. It turns out to be minus 1 to the m plus 1. So what is sort of interesting about this conjecture is that this is a C-finite identity in 2 variables, and that is not as routine to prove. In this case, finding a pattern of recurrence relations is not the same thing as proving it. You know, conjecturing a pattern is not the same thing as proving it, because it turns out that multivariable C-finite sequences are just more complicated than single variable, kind of like polynomials. So we can't just do this kind of, well, we had a list of examples, therefore it's true, because we had our list of examples and we don't have to do any other proof. So at this point, you might think, well, I guess I have to go do induction or a generating function argument or something like that. Or you did until we work out a theorem. So it turns out that if I have a C-finite sequence, any C-finite sequence at all, of course, the Fibonacci numbers are a good example. And I look at these dilations, these A of m times n. It turns out that they all satisfy a recurrence just from the closure properties, but actually they satisfy a uniform recurrence where the coefficients on the recurrence themselves are C-finite. And let me try and write that down in the Fibonacci example. So what this theorem says for the Fibonacci numbers is that the Fibonacci numbers, f of m times n, this satisfies a recurrence with respect to n that is uniform in m. That is, there's a formula for the recurrence no matter what m is. And it turns out that the coefficients on the recurrence themselves are C-finite, and they themselves satisfy a pattern. In other words, there's kind of a meta C-finite pattern going on. I take some recurrences of C-finite sequences and I find patterns between the recurrences themselves. So for the Fibonacci example, what it says is that the first coefficient will be some C-finite sequence of order less than or equal to 2 in the second. Was there a question? So the second coefficient will also be C-finite of order less than or equal to 1. So what's nice about this is that if you now go back to the list of examples that we gave, this actually is a proof now, because we just said that the coefficients will be C-finite sequences. And so if you can prove that if you can show that a C-finite sequence equals some other C-finite sequence enough terms, then they're always equal. So we showed that the first coefficient was a Lucas number for the first 5 values, and the second coefficient was minus 1 to the m plus 1 for the first 5 values. And this turns out to be enough terms to prove that they'll always be Lucas numbers, and they'll always be minus 1 to the m plus 1. So now we're firmly back into the case where conjecturing some patterns is the same thing as proving them. And you don't have to go break out induction at this point. This is totally fine now. Just write down some examples, go have lunch. No more thinking required. Now, you might ask, I guess, what's the idea here? What's going on? And the idea is actually not that complicated. It's really just this simple exponent rule for integer exponents. So I think we saw this a few times in talks yesterday and maybe earlier today too. Every C-finite sequence can be expressed as some linear combination of polynomials times exponential terms. This is a little hard to write down always, especially if your characteristic polynomial is really big, has a high degree, but in principle, this formula always exists. So if you write this down, then you can plug in a of m times n for n, and all you have to do is just group the exponents a little bit differently. And when you do that, and you think about it a little bit, it tells you that the characteristic polynomial of your C-finite sequence gets transformed. And how it gets transformed is all of the roots get raised to the mth power. Now, what's nice about this is if I now expand this characteristic polynomial, the coefficients will be symmetric polynomials in these roots raised to the mth power. And if I take some exponential terms, I add them, multiply them, subtract them, this is a C-finite sequence by the closure properties. So the coefficients on the characteristic polynomial will be C-finite sequences in M. And the characteristic polynomial essentially gives you the recurrence for your C-finite sequence. So this is the main idea behind the proof. And there's some small technical details to check, but this is essentially it right here. Now, this argument is simple enough that it actually applies to lots of other situations. You can also look at things like products of dilations of C-finite sequences. For example, f of I times n times f of j times n. And you can get other statements about having uniform recurrences. They're just a little messier, so I don't want to write them down here. And the nice thing about this method is once you have these uniform recurrences in two variables, you can often get some neat infinite families of results. You know, you have a recurrence, you can maybe go try and find some generating function, some asymptotics. And a little more interesting to me is there's some well-known tricks to turn recurrences into summation identities. I won't go through the details here, but you can actually prove this sort of famous identity about the sum of squares of dilated Fibonacci numbers by using this technique from my theorem to write down a uniform recurrence and then playing around with the recurrence. So there's a lot of neat infinite families of results that you can get from having uniform recurrences. And this theorem tells you that you don't need to sort of sweat to prove these uniform recurrences. You just need to find enough examples. This seems like a pretty good place to stop. So thank you for listening.
Any questions for our speaker? All right, so let's thank the speaker again.
Thank you, Steve.